Hello and welcome. In this episode, we're going to answer the question, how does the Earth move? Before we begin, please grab your packets and open up to page number 2. We'll be filling out the top half of this page through this video. So, how exactly does the Earth move? Well, as we know from our discussion of the solar system, the Earth and all the planets move in two ways. They all revolve around the sun, and at the same time, they rotate around their axis, or spin. Let's take a closer look at each of these motions, beginning with revolution. Here you see the Earth and its orbit around the sun. The Earth will complete one orbit or one complete revolution in about a year. Let's jot down some notes about revolution. Take a look at the top box on your handout. First thing is simple. We need to know that the Earth revolves around the sun. And one revolution of the Earth around the sun takes 365.26 days. Or a year. Now you don't need to memorize this number because it can be found in your reference tables. If you were to go into space above the North Pole of the Earth and the North Pole of the Sun and look down on them, you would see that the Earth revolves in a counterclockwise direction at a rate of about 1 degree per day. Now understand where this 1 degree number comes from. One revolution is essentially a complete circle around the Sun, 360 degrees. And it takes the Earth 365 days to do this. So if you divide 360 degrees by 365 days, you get a revolution speed of about 1 degree per day. Now, the revolution of the Earth has some major impacts on us, and these include all yearly changes. So if you think to yourself of any things that happen over the course of a year, any cycles that change yearly, most likely they can be traced back to the Earth's revolution. The most obvious example are the seasons. We know we go through a full cycle of seasons every year, so they are caused, at least in part, by the Earth's revolution. Another interesting change is the ability to see different constellations of stars at different times. If you go outside from New York in the winter, you will see the constellation Orion, but in the summer it's not visible as the Earth has moved. Let's draw a quick sketch with the sun in the center and the Earth on the side and the Earth's orbit. Be sure to include the arrow showing that counterclockwise motion. Let's talk about rotation for a moment. Rotation is the Earth's spin on its axis. We complete one spin every day. Let's jot down some notes about rotation. So the Earth rotates or spins around its axis of rotation. Now the axis of rotation is this imaginary line from the North Pole to the South Pole around which we spin. One complete rotation takes 23 hours, 56 minutes, and 4 seconds. But you could leave off the 4 seconds. Essentially, one rotation is 1 day. Now, if you were to look at the Earth from the side, at the equator, it rotates from west to east, and it spins at a rate of 15 degrees of longitude per hour. That is 360 degrees divided by 24 hours, giving you 15 degrees per hour. Now, while the revolution caused yearly changes, rotation causes daily changes. These are things like the sun rising and setting each day, the stars appearing to move across the sky, and a variety of other things, including day and night, the apparent motion of the sun, moon, and stars, something called the Coriolis effect, and Foucault's pendulum, both of which we'll discuss more in class. Let's sketch the Earth's rotation. Here's the Earth. You see the axis, this imaginary line through the North and South Pole, and you draw an arrow to show the west to east rotation. So let's take a moment and take a look at what all of this actually looks like. Okay, so here we can see the inner part of the solar system. Let me just turn the time on and get us moving a little bit here. And if you focus right here, you'll see the Earth, and you can see it rotating around its axis once a day. And at the same time that it's rotating, you can see by this blue path here, that is its orbit as it revolves around the sun. Now, in order to see a revolution take place, I will have to speed up time as it happens pretty slowly. It takes about a year. So I'm going to increase, let's do it daily. And here you can see the Earth spinning once a day, very quickly here, as it is revolving around the sun. Also notice some things we learned earlier on, which are that the planets closer to the sun, like Mercury and Venus, take less time to orbit, while as you get further out, they take more time. So there's the Earth rotating as it is revolving. I can turn this to the side a little bit so you can get a better idea of what it looks like, and I can zoom in so we can see what this looks like. Now as the Earth comes around the backside of the Sun here, I will slow it down so we can get a closer look at what the rotation actually looks like. So I'm going to stop it here, and we will go a little bit slower. And so here you can see the Earth rotating. And it is, though it doesn't look like it, it is still revolving around the Sun, but remember it's only moving about 1 degree of the complete orbit per day. So it's not a very noticeable motion. We are spinning 15 degrees per hour. We are revolving 1 degree per day. We are spinning from west to east, and from above we are revolving in a counterclockwise direction.
Right now, the Earth's surface is spinning at several hundred meters per second, and we're all along for the ride. It doesn't actually feel like you're moving though, which is nice, because being super dizzy all the time doesn't sound like a fun way to live. But that also means that for a long time we didn't know for sure that the Earth was spinning at all. People have suspected the Earth rotates for thousands of years, but it wasn't like they could just go to space and see for themselves, so it was hard to prove in a simple, clear way. Until 1851, when French physicist Léon Foucault hung a pendulum from one of the highest ceilings in Paris and let it swing. Before this, some astronomers as far back as the ancient Greeks thought the Earth rotated because that would explain why the Sun and other stars move across the sky. But not everyone accepted that. Most people believed that stars were attached to some kind of celestial sphere that spun around us, and it probably didn't help that some of the ideas about what caused the Earth to rotate were a bit odd. Finally, in 1651, an Italian physicist named Giovanni Battista Riccioli had an idea. He wrote that if the Earth rotated, a cannonball shot due north should curve to the right. It sounds like a weird way to explain the Earth's rotation, but Riccioli was on the right track. If you did fire a cannonball north, it would curve to the right, because of what we now call the Coriolis effect, although it wasn't named that until 200 years later. The Coriolis effect says that something moving in the northern hemisphere will look like it's being pushed to the right, and something moving in the southern hemisphere will look like it's being pushed to the left. Part of the reason for the Coriolis effect comes from the fact that the closer you get to the equator, the faster the Earth's surface rotates. That's because the planet is widest at the equator, so you have to travel farther to get all the way around it than you do closer to the poles. But it takes 1 day for the Earth to finish one rotation no matter where you are, which means the surface closer to the equator has to travel farther in the same amount of time, so it moves faster. Say you're standing at the equator and fire a cannonball north. The ball zooms north, but at the same time it's still moving east with the speed of the Earth's rotation at the equator where it left the cannon. That means that as it moves north, it's moving east faster than the Earth's surface. From your perspective standing next to the cannon, it looks like it's moving to the right. Unfortunately, or maybe luckily, physicists at the time didn't have much access to cannons. Besides, it would be tough to track the path of the cannonball and see if it curved or not. Now by the mid-1800s, most people did believe the Earth rotated because they'd finally accepted that Earth orbits the Sun. A rotating Earth was the best explanation for why the Sun and stars move across the sky, and they had some evidence for it, like from watching how the stars moved relative to each other. But it was still hard to prove in a clear, easy-to-see way, until Léon Foucault. In 1851, Foucault found a proof that could easily be repeated and didn't require any tall towers. He hung a pendulum from a string and let it swing. Since the pendulum is just hanging from the ceiling on a string, Earth's rotation can't force it to swivel. The ceiling it's attached to is rotating, but the string stays put while the ceiling turns around it. So once Foucault started the pendulum swinging, it just kept moving back and forth. But in the meantime, Earth kept rotating underneath it. From the perspective of someone standing on the ground, it looked like the pendulum swing was turning clockwise. That was the Coriolis effect in action. The pendulum swing didn't turn by much, but as time passed and the Earth kept rotating, its orientation changed more and more. Foucault first tested his pendulum in his basement and then in the Paris Observatory for fellow scientists, and it worked. Then he hung a 67-meter pendulum from the dome of Paris's Pantheon, a mausoleum for the greatest French thinkers, and showed it off to the public. For the first time, people could see a simple demonstration of Earth's rotation with their own eyes. Still, watching a swinging pendulum isn't something you want to do for hours, so to help them out, Foucault placed the pendulum over a bed of sand. As the pendulum swung, the tip traced out a line in the sand, and over time, the line showed the pendulum was no longer swinging in the same direction. You can find Foucault's pendulums in science museums all over the world, and even though they might seem like just a cool party trick now that we can see Earth rotating from space, they were really important for helping us understand how our planet works. The only people who weren't excited about Foucault's discovery were the scientific elite, who were annoyed by his lack of traditional scientific training. Unfortunately for them, that didn't change the fact that Foucault created the first simple, clear proof that the Earth rotated. But maybe they were just mad that they didn't think of it first. Thanks for watching this episode of SciShow. If you'd like to learn more about the Coriolis effect, you can watch our episode about how it might not mean what you think it means.